Okay, good morning, students. So, as promised in class, I will be going over some of the problems on homework. I won't be going over all of them. I chose some that I think would be most helpful for you guys for me to go over. So, the first one I thought of was which of the following pairs of structures represent resonance forms? So, for this one, what you have to keep in mind is there are constitutional isomers, sorry, conformational. And so these ones, they have the same formula, molecular formula. But what they differ in is how the molecule is attached. So, conformational isomers are very different than resonance structures. Okay, because resonance structures they have the exact same atoms and in the same order, same connectivity. The only difference is they differ in movement of electrons, and especially or specifically pi electrons. Okay, the pi electrons are the ones that can move around. Thus, that's what resonance is. Conformational isomers are going to be, they have same formula, but different structure. Okay, so looking at this first one, the difference is at the beginning we had this bond here. However, it's not there on the second one. Okay, and instead, now we can see the double bonds are in different spots. Oh, there's my laser. Okay, so again, we had this bond here. We had three double bonds in here. However, on this one, we move the pi electrons and we don't have that bond anymore. So because of that, this one is going to be conformational isomer. So not resonance. Okay. Now let's look at the second one. So on this one, I can see I have this oxygen with a negative charge. I have a double bond here. Okay, and on the second one, I have a double bond here and a negative charge here. So the two molecules, they have the same atoms, the same order. The only thing that's different is where that negative charge is and where the double bond is. So we need to see if this is a resonance structure or not. So if I look at here, I have this lone pair. If I move it down, I can move it right here, and I can move these electrons onto the carbon. And if I redraw it, that will make this molecule. So this one is a resonance structure. Okay, so this one right here is a conformational isomer because the connectivity between the two molecules are different. This one has the same connectivity. Okay, all the atoms are bound to the same thing. The only difference is going to be those pi electrons. So because of that, this one is going to be a resonance structure. Okay, now let's do the second problem. Okay, on this one it says draw as many resonance structures as you can for the following species. And I'm really sorry, you guys. I didn't leave enough room, but we're gonna try our best. Okay, so let's do just one of these. So I think the main challenge with these is they are drawn a little differently. So it might be some of them it might be easier to redraw them, just that you can see them in the way we typically see them. However, I am going to do, let's see, I'll do this one. Okay, the one with a bunch of nitrogens. So on here, I have a carbon in the middle, I have nitrogen up here, I have a nitrogen over here with two hydrogens on each of them. And then I have a nitrogen with a double bond over here with two hydrogens as well. Now, the difference is this one has um, the positive charge. Okay, now these two have lone pairs on them, so don't forget that. Whereas in the last nitrogen does not. It has that positive charge. So first thing we can do is we can bring the double bond onto the nitrogen. The nitrogen has a positive charge. If we bring the electrons onto the nitrogen, that's going to make it a neutral charge. And it won't break any octet rules because the nitrogen still has 8 electrons. The only one that's missing electrons now is going to be that carbon because it lost electrons. Let me just move this one a little bit up and make it smaller. Let's put these back. Okay, cool. Okay, so I still have nitrogen, 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 H. Draw on all my hydrogens. They're not carbons, so I have to draw on all the hydrogens. Okay, and the carbon in the middle now has a positive charge because it's missing electrons. So what can happen next is this nitrogen over here can donate electrons to make a double bond. I'm going to put this over here. Also, don't forget those double-sided arrows to show that it's a resonance structure, okay? Just to make sure that it's not a new molecule. So I'm going to draw in my basic. I'm going to start putting NH2. It's just smaller and easier, okay? But on this one, I'll put the double bond, nitrogen, HH. So as you can see, this one now has more electrons on it. Less electrons directly on it, as it's sharing those electrons with carbon. So that one's going to have a double bond as well. Now this nitrogen down here can now donate as well, moving those electrons onto the carbon, or making a double bond with carbon. And instead of drawing it as a separate step, I'm going to draw it as one step. So that nitrogen, those electrons move up onto nitrogen. Okay, so as we can see, they're all very similar. It just depends on which nitrogen has that double bond and which one doesn't. And depending on which one has the double bond, that one will have the positive charge, or it'll be on the carbon. Okay, so we can draw those 4 different resonance structures. Each of them are a little different, so make sure to draw all of them. Okay, and then if we want to draw the resonance hybrid, which is actually a good idea to get that practice in, I'm going to draw the skeletal structure, drawing those nitrogens. H2, don't forget your hydrogens. Okay, and now I'm going to draw in dots wherever the double bonds were. So I know there was a double bond here, there was one here, and there was one here. As we saw, each nitrogen made a double bond with the carbon. Now the partial positives, which are delta positives, are on the nitrogens. As we saw, those ones each had a positive charge at one point. Okay, and then don't forget, the carbon also had a positive charge on it. So that one's also going to have a positive charge. Okay, so that's going to be our resonance hybrid right here. Okay, now let's go to the next one. So I wanted to do this one. I think this one talks about valence electrons as well as VSEPR. And so it's a nice review of Gen Chem 1 things that we may have forgotten. So the first thing it says is how many electrons are in the valence shell of carbon bearing the positive charge. Okay, so we can see that we have electrons here, here, and here. Okay, but we do have a positive. Okay, so each of those bonds has 2, so 2 electrons, 2 electrons, and then 2 electrons here as well. So it looks like this one has 6 electrons. Okay. And so that's why it has that positive charge, because it's missing electrons. And we could even do the formal charge to double check if you want to. So the formal charge is going to be 4 valence electrons minus 3 bonds minus 0 lone pairs. So we can see that we get a 1. So it should be positive charge. So that matches up. Okay, next thing is using VSEPR, predict the bond angle about this carbon. You can do bond angle or the shape as well. So as we can see on the molecule, okay, let's clean it up a little bit so we can see it better. Okay, there's 1 bond, 2 bonds, and 3 bonds. And each of those are going to be an electron group. So we have 1 electron group, 2, and 3. We don't have a fourth one because that positive charge tells us there's no lone pairs. There's nothing else on there. So it's just going to be 3 electron groups, which tells us that we're going to have an trigonal planar. Okay, and if we're thinking about hybridization, this one will be an sp2. Okay, good. Now the next question I wanted to go over is going to be this one. Okay, on this one, it says to draw all the resonance structures, okay, and show the arrows. Okay, and then decide which one is going to be more stable. So for this first one, most people are going to want to just use the drawing as is. However, I would highly recommend that you redraw it so that way you can see what the full structure is. Because if you don't, you're going to miss it. If you see here, this carbon is only attached to the oxygen and to the carbon. So because of that, we know that this is going to be a double bond. It's the only way that we can get enough electrons, or enough electrons in the valence, sorry, the only way that we can fulfill the octet rule for oxygen and carbon. Okay, however, on the other one, we can see this oxygen and this carbon, there's more hydrogens between them. So on this one, it is a different structure. So if we draw it out, it'll be O, oops, I forgot a carbon. Carbon O, this one, okay? I almost forgot that carbon. Make sure to have a line break before going to the oxygen. Okay, so as you can see, these two are very different. They look very similar when they're written out, but now that we have the structure redrawn, you can see a bit more of how they differ. So for resonance, both of them can resonate this way and make those electrons go up on the nitrogen. Okay, they're both exactly the same on that because the structure is the same for both of them in that regard. Okay, because of that, the nitrogen now has that negative charge on it. So it has two lone pairs. Sorry, it has, yeah, 2 lone pairs now. Okay, and on the other side, nothing changed. So we just still have the oxygen with a double bond onto carbon. Okay, on this side, similarly, okay, no change on the oxygen side. The change is going to be with that nitrogen. As you can see, this arrow tells us that we made a double bond onto that carbon-carbon. Okay, let's draw that. Oh, I can't draw a straight line, you guys. Okay, that's going to be close enough. And then we follow this arrow showing that the double bond now became a lone pair on the nitrogen. Okay, so negative charge on the nitrogen. And if we're not sure, we can always double check the formal charge. Okay, so all that is the same, but now let's see if there's any other way to resonate. So for example, if I bring these back down, I can now move these carbons over here because this can also move on to the oxygen. Okay, if I try that on the other side, it's not going to work because this carbon has 2 hydrogens. So because of that, this carbon has no pi electrons, so there's no way we can resonate onto that. So this resonance structure doesn't work. Okay. However, on the one above with that double bonded oxygen, that one's going to work. So we're going to draw in this new resonance structure. Okay, it's going to look like that. So because this one has more resonance, we can tell that it's going to be more stable than the other one. Okay, it has that extra resonance, and also the resonance goes on to the oxygen, so that one's going to be the most stable. Okay, and that's going to be it for that one. Thanks, you guys.